let's start exploring. Let's like diving deep into these complexity classes, these animals in cages in this complexity zoo, of which you are the zookeeper. I'm coming up to the first cage, and I see this animal called the P complexity class.
Yes.
What is the P class?
Okay, so P stands for polynomial time, and it is the class of all the problems, technically all the decision problems with yes or no answers, okay, that are solvable by some algorithm running on a digital deterministic computer, like that one, or like the ones we all have in our pockets, in polynomial time, by which we mean, the algorithm has to get the right answer for every possible input. Okay, so it always has to work, and it has to halt after a number of steps that grows only like the input size raised to some fixed power. So this is sort of our rough and ready approximation to what set of problems are efficiently solvable by a standard digital computer. Okay, now it's not a perfect a representation of that, because, for example, if we said n to the 1 million power, right? Well, formally that's a polynomial, but in practice, that you would never want to deal with that, right? So what justifies this definition in practice, the reason why people adopted it starting in the 1960s, was that it turns out that most of the time, when there is a polynomial time algorithm to solve some problem, then the degree of the polynomial is quite small, or can be made small, right?
It's bounded.
So usually when we see problems in P, there is an n squared algorithm, maybe an n cubed algorithm, and only rarely is it worse than that, right? But even when someone discovers that a problem is in P by finding an n to the 10 algorithm, let's say, very, very often, if they put enough effort into it, they can make it n to the 5, and then they can make that n to the 4, and so forth. It's sort of like, you're at least within striking distance of, like I like to say, like if you're Odysseus, you've won the Trojan War, right? Now you just have to find your way home.
Right.
Right.
Okay.
So examples of problems in P, right? P actually includes most of what we do with our computers on a day-to-day basis. Okay, so pretty much every basic arithmetic operation is going to be, correspond to some problem that's in P. Multiplication, division, also, greatest common divisor, reducing a fraction to lowest terms, finding the shortest path, in a graph.
This is Dijkstra's algorithm.
Yeah, exactly. Yeah. So let's say the kind of thing that Google Maps does when you ask it for directions, that corresponds to a problem in P, okay? And then, a bunch of things that are less obvious. Solving systems of linear equations, okay? Even solving systems of linear inequalities. That's called linear programming. Right, that's also in P. Okay, that took people decades to prove, but we in the 1980s we learned that that's true. Determining whether a number is prime or composite turns out to be in P. Okay, and that was suspected for a long time. It was only proven in 2002 in a breakthrough by Agrawal, Kyle, and Saxena. Kyle and Saxena were undergraduates at IIT Kanpur at the time that they produced this breakthrough. Okay, and notice, I said determining whether a number is prime. You might say, well, didn't we just talk about factoring, right? Well, so what we know to be in P is only to determine is your number prime or composite, right? The algorithms that we know, if the number is composite, they just tell you that. They give you no hint about what are the prime factors. That still seems to be a much, much harder problem, right? So, this is a beautiful example of how the boundary between what's in P and what's not in P can be extremely non-obvious, right? Like, determining if a number is prime is in P. Factoring a number, well, we don't know, but, we base the whole security of the internet on the belief that problem is not in P. So that's P.